So first of all, maybe we need to understand or to take note about this subtopic. The reason being this topic is included into this chapter is to facilitate, okay, to facilitate the handling of a block diagram manipulation. So if we could not, or we cannot find, we cannot manipulate, we cannot handle the block diagram um, effectively, we can resort the handling technique based on this signal flow graph. So we can further simplify the procedure in getting the transfer function by using nodes and also simple uh, steps where it is introduced by uh, J. Mason, S.J. Mason. And now, if we consider a simple block diagram which is come from mass spring system. So a mass spring system is given by this block diagram here, right? So this is a mass spring system, right? So the mass spring system block diagram can be transformed into a signal flow graph as illustrated in this figure here. So in order to understand the um, concept of signal flow graph, we need to take a look at the definition or terminologies of the components that a signal flow graph uh, has. So the first one is node. So node is basically a point that represent a variable. So variable in this sense is a signal, how much the signal has changed from one point to another. For example, at this node number one, node one, it carries this signal that come from RS, right? And then once it reach to N2, it still carry the same signal RS. Why? Because the there is no changes that occur from node 1 until node 2, and these changes basically can be defined by, or can be illustrated by the gain that the transfer has inject into the node. For example, RS from N1 um, will go into transfer of 1, and thus at N2 it still carry the same signal of RS. But when the signal of RS go to N3, it has to pass this N1 upon M, and thus the signal at N3 is no longer the same as RS. Instead, it is combination of RS and also 1 upon M, and similar goes to N3 to N4, and then N4 to N5. It is a combination of a transfer and the signal of the previous node. Okay, so what is meant by transfer is basically a gain between the two nodes that I mentioned just now. And then we have entry node. So entry node is, in this case, is N1, and this entry node is always independent variable. And then we have exit node. Exit node is a dependent variable. It can be N4, it can be N3, as long as it is dependent to something or dependent to other nodes. And clearly, if we consider the figure 2.6, the dependent variable can be n5, n4, and so on. And then we have definition of fault path. So fault path what is meant by fault path is a network that connected that with nodes that is in straight line, in straight path. So for example, from n1 until n5. So this network with nodes of n1 until n5 is known as forward path. Okay, and then we have loop. So loop in this case is highlighted in orange color. Okay, so it start from n3, go to n4, and then go back to n3. So when it go back to n3, it carries a gain that is specified in this expression here, right? And then we have final definition, which is non-touching loop. So non-touching loop can be illustrated by this figure 2.7, where we have two loops. Okay, so loop number 1 is n1 to n2 to n3, and then n3 back to n1. So in terms of gain, this loop has a, b, g, and then the other loop is starting from n4 to n5 and back to n4. And in terms of gain, this loop has df. So the nodes on the first loop is not touching the nodes on the second loop. So as we can see here, n1 belongs to loop number 1, and it is not shared. It's not being shared with loop number 2, because loop number 2 start with n4 and then n5 and back to n4. So this is the illustration of non-touching loop on the same forward path with n1 until n6. Right, and then to determine a transfer function from a signal flow graph, we need to make use 5 simple rules where we make use the definition of gain, the definition of the forward path, and then some additional component, which is for example determinant and the individual determinant and Mason rule. So Mason rule is basically the formulation that is used to obtain a transfer function. So we will see this in more clear steps when we consider a work example in the following section. Right. So to help us in manipulating the signal flow graph more effective, we can make use the equivalent table, which is illustrated in table 2.2. So these are the essential block and its corresponding equivalent signal flow graph. So on the left hand side is the block diagram. On the right hand side is the equivalent signal flow graph that we can consider in generating or in transforming from, if we have a block diagram and then we want to convert this block diagram into signal flow graph, we can consider this table. And this table will facilitate us in determining the correct signal flow graph